And that's the easiest way to take $10 and turn it into 10,000. Cool. All right. All right. Acids and bases. We've spoke about these at least briefly in here. Maybe we didn't. I don't think we wrote anything down. What's the difference? Acid and base.
Acids like stomach acid, so like dissolve stuff.
Okay, but I think that if I put something in a bucket of bleach, you could probably dissolve stuff in there too. And bleach is not an acid, so that's okay. Like, we're covering it now, right? In physical science, you guys probably talked about it a little bit. We're going to look at something, and all of this focuses around, and I wish I could give you the true meaning of this. Unfortunately, I can't, nor can anybody with confidence. Okay, we're going to be talking about this idea of pH. Measured, acids and bases are measured by pH values, and it's a lowercase p and a capital H. Now, the lore or the legend behind this stuff is pH. It has a very specific thing that we're representing, and there's a lot of math that goes into it. Eventually, it's not going to be in here, but it just depends on how acidic or how basic is something. That's all it tells us. And the person, the chemist, the physicist who first started looking at pH stuff and measuring it was French, and he didn't write a lot down with regard to what this stood for. He just said, here's pH and here's how I calculate it. Never said exactly what it was, or like what those words or letters meant. So the pH is kind of lost to history at this point. Now, in the chemistry side of things, there's a couple different ways that we can think about this. So we're going to first look, and we're going to see both of them, and we're just going to sneak the vocab in with this, and then we'll summarize it at the end to make it a little bit easier to think about. So right off the bat, our first little topic, let's say that we have a substance that's dissolved in water. So a substance, or whatever it is, a substance dissolved in water and we're just going to pause right there so that we can catch up because there's a lot more talking than writing today. Cool. I've dissolved something in water. Water has a lot of special properties. Can you remember the one, something about the charges of a water? Like it's almost like a magnet is how we were thinking about it in here.
Oh, is it like medicine? Like it could be different forms.
So that's awesome. Those are great statements. It definitely happens. Not what I'm looking for, but yes, absolutely, that's true. When we look at water, remember what makes water stick to other water? Love it. The fact that one side of a water molecule is positive, it's the hydrogen side, and one side of it's negative, that's the oxygen side. Okay, when we look at water then, if we mix something else with it, is it possible that the thing that we mix with it has some hydrogen in it? Like lots of stuff has hydrogen. Water has hydrogen. There's tons of things out there that have it. Now, hydrogen wants to gain electrons. That means that it tends to have a slight positive charge to it. Okay, that means that it gets pulled off of whatever it's in and it joins to the water. So it's just these magnets moving around. Water pulls on them, and sometimes they pull them off of whatever it comes from. When this happens, if a substance dissolved in water releases hydrogen atoms, and we're going to be even more specific, a substance dissolved in water releases hydrogen, and I'm going to say ions, and I can spell this, I promise. Hydrogen ions, which again, there's lots of little pieces. I'm going to pause here because we've talked about it. We're not going to redefine it. Do you guys remember what an ion is? Check. Go through your notes if you need to. I'm fine with that. Hydrogen likes to become an ion. And before you look, just real quick, and I guess, no, keep looking. I lied.
An atom that has like none or less electrons than the proton.
Okay, perfect. Now, most of the hydrogen in our universe doesn't have electrons. Like, it's okay to not, sorry. Most of it doesn't have neutrons. Hydrogen can do one of two things. It can either ditch an electron, and it'll be balanced. That nice, it's a weird rule with that first row. Or it can gain an electron. Now, it turns out that in some situations, it's much easier to get rid of that electron. If you had a hydrogen atom that was a neutral charge, because it had one positive and one negative, and you lost your electron, Now there's only one positive charge left. It becomes positive. Are you guys okay with just that thought? If I'm balanced and I get rid of the negative charge, all I have is positive, I'm now positive. That's an ion. Okay, so when we talk about this, a substance dissolved in water releases hydrogen ions, which the way that we're going to denote this, what's the letter for hydrogen? Okay, and if I want to indicate that this thing is positively charged, I'm just going to write a plus right here. Okay, it releases hydrogen ions that are positive, and they join with the water that has a negative end on it. When we look at this, we'll even say and justify a little bit further, due to the negative polarity or the negative charge of oxygen, specifically in water, but I'm going to write in H2O. Okay, negative side of the oxygen sometimes will pull positive hydrogen ions off of whatever's being mixed in. Okay, this happens. There's craziness going on there. Cool. This thing, as soon as this happens, we start to get more and more positive hydrogen atoms or ions that are stuck to my water. This right here is an acid. So without going like crazy with it, I'm going to say that this is an acid. An acid is something that gives up its hydrogen ions. Now, for this, there's a bit of chemistry going in there with it, which you may love or hate or don't really care about. But here's the deal. If you have a bunch of H plus that fall off of whatever you're mixing with water, you get an acid. So orange juice, for example, is acidic because if you make orange juice, a bunch of those hydrogen atoms get pulled off and they become positively charged. They attract to the oxygen in an H2O. For this, we're going to make a kind of follow-up statement. As the number of H plus atoms or ions of H plus increases, it has an impact on the pH. And we're going to write out that impact here in just a second. Now, for this, I'll wait till everybody's done writing so you don't have to try to do both. We're not talking about if I add more of the substance to water, more ions come off. We're not talking about that ratio necessarily just increasing, because if I have 5 hydrogen ions that get released from this and I double the amount, then 10 would come off in more water. Like that's the same level, same ratio. However, if I put substance 1 in water and I get 10 of these hydrogen ions, and I put substance 2 in, a different substance, and 50 of them come off. There's a noticeable difference between those two substances. For this, as the number of those ions that get pulled off increase, the pH decreases. Okay, so more hydrogen ions present, lower pH. That's all that this statement means. Now, we'll look at the numbers here in a second, but there's a flip side. Sometimes the negative charge of the oxygen in a water pulls off hydrogens. Okay, but water is polar. The oxygen is negative. The 2 hydrogens on the other side of it make a positive charge, right? Slightly positive. They're not going to attract positive hydrogen, right? Because positives and positives don't attract. In the flip side of this, and this is a much shorter substance, other substances, so if they get rid of their H plus, it's called an acid, and the pH gets lower and lower and lower. Other substances, instead of releasing the positive, they release a negative. So other substances release a different type of ion, and we're going to write this out. This is OH negative. Okay, for the record, OH negative, it has a name. This is, and you should have it, but I'm not going to quiz you on this. This is called hydroxide. This is an hydroxide ion because it's now negatively charged instead of being balanced. Other substances release this. Notice it's the exact opposite. I either release a positive ion to make it acidic, or I release an OH negative ion, which makes it the opposite of acid, which is what do you think? Bases. Base. And the way that this is written on my screen is going to bug me, so I'm just going to copy. Actually, I'll just move this. I'm going to move that there because it's going to bug me there. Okay. This, for the exact same reason, but it's not due to the negative charge of oxygen. It's due to the positive charge of the hydrogens on a water. Okay. This is a base. Okay. So we're either going to release hydrogen and become an acid, or we're going to release hydroxide and become a base. Those are the two options. Now, similar statement. As the number of these hydroxide ions, OH negative, increases, the pH, and we're going to just deduce out this. If I release a bunch of H+, it becomes lower pH value. What happens if I do the exact opposite? What do you think happens to the pH? So if I release positives, it decreases. What if I release negatives? Increases. The pH increases. Now, you guys are in geometry, right? Okay. Without any expansion, just out of curiosity, geometry or algebra. In Algebra 1 or geometry, have you ever heard the word logarithm? Okay, so we won't even discuss it. Okay, this is a base. Now, as we look at these, there's an easy way to summarize. I want you to be aware that it's H+ that makes it acid and OH negative that makes it base. Like those I want you to know. That's fundamental to the chemistry that's happening here. In reality, the pH scale doesn't go forever. I can't have a pH of 50. That's insane. I can't have a pH of -13. That doesn't mean anything at all to me. So, real quickly, we'll summarize here. pH is a scale, and I'm going to add a word here. I'm going to say logarithmic, which the understanding that we don't really have a true understanding of it is a logarithmic scale. Okay, where, and we're going to list out a few important parts of pH. Do you want to talk really quickly without going into the mathy part of logarithms? All right, so check it out. This is going to feel like a math question, but it's not super mathy. I want you guys, what is the number that is, what's the number between or in the middle of 4 and, 2000's too big. Let's do 4 and 8. What's right in the middle of 4 and 8? 6 is a pretty natural thought for Americans and Western stuff. Other places in the world, you're going to get a different answer. And they're not wrong. They just think about numbers fundamentally differently than we do. In huge parts of Africa, somebody between 4 and... I got to pick different numbers. I'm sorry. I'm making this up off the top of my head because I didn't know how much you guys had logs. What's right between 4 and 16?
8, 12,
I would say like 11.
12.
How'd you get your answer?
Wait, what was it you say?
4 and 16.
4 and 16.
Between 4 and 16.
4 and 16. I would say 10.
10. How are you doing it? I think it's 10 from my point of view.
2, 4, 6.
Because 6.
The difference between 4 and 16 is 12, and half of 12 is 6, so I start at either end, I go 6, right? Okay, that's how I think about it. Like, I physically see a number line in my head as I think about these. Do you guys? Cool. A lot of people don't see pictures in their head. Like, much more common. When I think, I see pictures. Some people see words. Some people see nothing. I can't see nothing in my head. That's what I'm fucking on. Anyway. Okay. We all agree that 10 is halfway between 4 and 16? Okay. Some places will say, no, that's not true at all. It's 8. And I think they're also right. Now, we think regularly we just go one number at a time, right? But if we look at this, 4 to the first power is 4, right? Or 2 to the second power if we word it. 2 squared is 4. 2 to the fourth is 16. And I'm just telling you guys that's true. 2 squared is 4. 2 to the fourth is 16. What's between that square on 2 and 4? What's between 2 and 4 is the question I'm looking at.
Three.
3. What's 2 to the power of 3?
One.
2 times 2 times 2.
Wait, what does power mean?
It's just multiplied by itself this many times.
Oh,
So 2 times 2 is
4.
times 2,
Eight.
8. So some places they don't think about the numbers just as themselves, but they think about them as powers of other stuff. And that idea is known as a logarithm. And I'm not going to go any more into it. There's lots of stuff that's a log scale. Earthquakes are a log scale. And they're called log base 10. Let's say I had a magnitude 8 earthquake. It's pretty strong. A magnitude 9 earthquake is how much stronger? Like, if I measure the energy, how many more times of energy do you think there is in a magnitude 9 compared to a magnitude 8? It's a total guess, I'm sure of it. Louder? What did you say? What was your number? You made a noise though, right? Okay. I thought it was going crazy. What's your guess? How much stronger is a magnitude 9 than a magnitude 8 earthquake? So 100 is pretty close. Like, that's a good guess. I'll tell you that's too big. It's 10. 10 times stronger. A magnitude 7 earthquake and a magnitude 9. 100 times stronger. Magnitude 5 and a magnitude 8. How many magnitudes away from each other? Between 5 and 8? 3? I'm going to say it's 1,000 times stronger, a magnitude 8. We're working with powers of 10 is all I'm doing. Every 1 point you go up on the Richter scale, how we measure earthquakes, it's 10 to that number bigger. So 10, that's a lot. Anyway. Okay, for this, it's natural to scale things up bigger. Okay, pH is logarithmic. Where? We're just going to list this out, and I'm going to leave it blank, leave a space to write something. pH equal to 7 is neutral. If you have something that has a pH of 7, you would not say that it's a base. You would not say it's an acid. It is exactly in between them. Okay. Now, we said that if we add, the more H plus that we get, what happens with pH? It decreases with H plus, right? So that means if the pH value is less than 7, that's been a decrease, right? What is this then? Is this an acid or is this a base? Which one was decreasing? This is acidic. Okay, anything with a pH less than 7 is acidic. Which means on the flip side of that, if we take a pH greater than 7, it's what? It's a base. Now, we deal as humans, and I think that feels like I had this comment the other day. As humans, we deal better with acids than we do with bases. Okay, I can drink a acid with a pH of 4 as long as it's not like a toxic acid. Like orange juice is probably around 4 or lower. I can safely drink that. However, I cannot safely drink something with a pH of 11, which is the same distance away, just in the base direction. I cannot drink that safely. I'll probably die. Our bodies can't handle bases well. Okay, pH stuff exists, and remember that with enzymes, pH of our body is one of the things that winds up impacting this. Now, beyond that, cellular processes, and this is the last statement that we're making, and you guys are going to have some time to work on stuff. So just a couple additional little follow-ups. As we look at this, most of our body has homeostasis at specific pH values. Humans, and I'm going to say human, I think just works. Biological processes. Biological processes work best when we have a pH that's in a range of not too wildly far away from neutral. Our bodies want our pH to be bigger than 6.5. So we're going to write a compound fraction. pH greater, I lied, or pH less than 7.5. So our bodies are cool to handle stuff on a cellular level, like inside of our cells. If you were to check the pH of the liquid that's there, it's going to be between 6.5 and 7.5, either barely acidic or barely basic. Anything outside of this, can cause some chaos in us. Now, in our cells, like I drink orange juice that has a pH well below 7. My body then has to take that and fix it, because if I introduce that into this process, I think, correct me, like double check my math, is 4 outside of this range? 4 is not between 6.5 and 7.5, yeah? Like it's just not there. Which means our body has to take whatever we ingest and fix it. Buffers are what the things in our body, without a ton more detail, buffers is a word that we use. We buffer the pH of whatever we ingest to make it fit our body. Buffers change pH in our body. And in fact, if we went over to my lab next door and looked through my cabinets, you would find a bunch of stuff that says 4.0 buffer or 7.8 buffer. Like it's things that make the pH this value. Buffers adjust pH in our bodies and in the lab. pH. Okay. Now, these buffers are mixtures and they just take things and change the pH. Cool. That's all I have for this section. Awesome. Cool. So just for fun, let's just check some of these. You guys are going to have some homework, and fun is just for, I don't know how to word it. Well, whatever. We're just all going to have fun, right? Yeah, we always have fun in here. Check it out. Your guys' homework is going to exist on page 150. So this is homework 6.3, page 150. And let's see, you get the privilege of, ooh. You're going to have to use a picture on one of them, just so you know. But if you're looking in your book, it's there.
We're going to have to draw the picture.
Yeah, a small picture. I want you to do 1 through 6.
We always tear off homework, right? Or this one?
Always tear off homework. Now, I also want you to do the vocab. And vocab. Okay, your guys, I'm going to let you help me decide. Is this one assignment or is this 2 assignments? 2 separate assignments? Do both of them. If somebody didn't hand one in the other day, I put a 0 in the grade book. And because we only have like 4 or 5 grades, if I put a 0 in the grade book, what happens to your grade? It kills it, temporarily. Now, I don't think anyone here deserves an F, but I do think that if you haven't handed something in, that's probably where you're at right now, just off the top of my head. Do I take late work?
Yes.
I do. When?
Like a week, only for like a week period.
So that's not right, but that's okay. Do you know how long I take late work for?
3 days.
Where are you guys getting these numbers from? Okay, that's fair. I will take anything late from chapter 6 until we take the chapter 7 test.
Oh, so you'll take anything from
I will take anything from chapter 6 until we take chapter 7 test with the following just agreement. If I learned something today and I blow off the assignment and I do it tonight, or if I learned it yesterday, I didn't do the homework and I did it tonight, it's going to be okay. But if I blew it off yesterday and then I wait 4 weeks to do it, is it going to be easier or harder? Oh my gosh, because I'm not going to remember everything, because the point of the homework is to help you guys remember stuff. Like, you don't remember everything perfectly. You shouldn't. I mean, I wish you did. I don't. Cool. All right. You had a question that seemed. Yep, make sure you sign out, okay? You remember the policy, right?
I got a
-1 participation
What?
is what it takes.
But we're doing homeworks now.
Yeah, that's a good argument. We're going to keep that argument. No, you're good. We're going to keep it in here. Go to the bathroom. Okay. Cool. I want you guys to start working. The picture that I referred to is figure 28 on the same page. And you'll see it. It's number 3. You're going to look at figure 28 for number 3. You don't have to write this part. I just want you to see it. Cool. I'm going to give you guys some time to work on it. Would you like to see the awesome new music that I stumbled upon yesterday? So check it out. Do you guys know My Chemical Romance? Maybe not by name. Okay, so they were like I don't know. Do you guys still use the word emo?
Yes.
Okay, so I wouldn't call them emo, but you guys might, because nobody ever gets emo right. But that's okay. Looking at their band from the early 2000s, and whether you recognize them by name or not, whatever, you probably recognize the song. When I was a young boy, my father took me into the city to see that. Do you recognize the song or no? Okay, well, weird. First hour, everybody recognized it. That's okay. I found some covers that just randomly showed up, and I sent it to Miss Val, but I'm going to make you guys listen to this awesome cover that I found. Cool. We'll listen to it while you work.